Hi everyone, it's Wednesday. Welcome to the live stream. I do want to check and see how my volume is doing because I feel like it's maybe a little bit on the low side. Anyway, let me know. OG Benchmarks, I know, will let me know if that is a little bit on the low side. Anyway, so this week I thought we'd continue with acids and bases, but this time we would continue with weak acids and bases. So this brings up having to deal with acids and bases, but also having to deal with equilibrium that's happening when we have weak acids and bases. But as usual, maybe a bit more volume. Okay, I'll try to give it a little bit more volume. I think I can control it maybe down here. Okay, so that ought to bump me up a little bit. So hopefully that's a little bit better. Unfortunately, that's about all I can give you out of this one. Maybe I'll bring the microphone a little bit closer to my face there. Whoops, sorry, that muted it. Yeah, unfortunately, this microphone is at 100% here, so I am not sure why it's not giving me more volume. I'll bring it a little bit closer and try to speak a little bit louder too, so hopefully I can be a little more clear. Okay, it's better. Good. Okay, so I know, tech issues, I'm getting confused. Let's go ahead and just jump over here and let's start with our weak acids and bases. All right, so what I wanted to do, of course, is start with some definitions. What is the difference between a weak acid and a strong base? And a strong acid, what is the difference between a weak base and a strong base? And you can see I wrote the definition right here. So a strong acid or a strong base, because definitions are the same for that, these are molecules that are going to completely dissociate, or we say completely ionize in aqueous solution. So we saw this last week actually. So for example, hydrochloric acid, when you put it in aqueous solution, it completely dissociates into the hydronium ion and the chloride anion. So what I want you to notice is I just have the right hand arrow. So this reaction simply proceeds forward. There is no reverse reaction that happens. Okay. Now, to contrast that with a weak acid or a weak base, let me switch back, is a molecule that's only going to partly dissociate or partly ionize. So if we're going to go back to an acid, let's take a look at hydrofluoric acid. When you put it in aqueous solution, and you notice I use equilibrium arrows. This is because hydrofluoric acid is a weak acid. Some of it is going to dissociate to form hydronium ion and the fluoride anion, but some of it is going to stay as HF bonded together. This is what we mean by partially dissociate. And really the thing that you want to look at is the difference in the arrows. So a strong acid or a strong base is only going to have a right hand arrow. So it only proceeds from reactants to products. That's it. If you have a weak acid or base, you have both the forward and the reverse reaction happening. It is in equilibrium. Oh, I guess I should go ahead and maybe write, so this one is strong. This one is weak. Let me give you an example of a base. So strong base, sodium hydroxide. I mean, this is the classic. Again, only a right-hand arrow. It's going to completely ionize, meaning that in solution, you don't have sodium bonded to hydroxide anymore. You have sodium cations and hydroxide anions, as opposed to ammonia, which is a weak base. And so again, notice how I put the equilibrium errors, meaning we have a forward reaction and we have a reverse reaction happening. So this will give us the ammonium cation and the hydroxide anion. Okay, so let me label these again. Strong, weak. Okay, let's make sure. All right, yes, that we didn't have any questions. I thought I saw something pop up over there. All right, so what I also did here at the bottom of the screen was I put in some common strong acids and some common strong bases. And a lot of times in your class, depending on your teacher or your professor, they might have you memorize especially the strong acids. And so if you don't have a strong acid, then you assume it's a weak acid. Another thing you can do is if an acid has a Ka value, then it is a weak acid. So if you try to look up the Ka value for hydrochloric acid, you're not going to find it. At best, you'll find something that says strong, or maybe it'll say large for a large Ka value. So why is that? Well, let's talk about how to write Kas and Kbs. So let's write our Ka for hydrofluoric acid. So when you write an equilibrium constant, of course, you're going to put concentration of products over concentration of reactants. So again, if I'm looking at this hydrofluoric equilibrium here, this is going to be the concentration of the hydronium ion times the concentration of the fluoride anion over the concentration of hydrofluoric acid. That is an H. It kind of looks like a 4. All right, now, the one thing I do want to point out is what happened to the concentration of water. And a lot of times we fudge this a little bit by saying, well, pure liquids and solids we don't include in equilibrium constants, which is generally true. However, in this case, because we are dealing with a Ka, the concentration of water is actually included in this value because it is a constant. It's like 55 molar. OG benchmarks, you can help me out with this. I think it's 55 molar. So because that concentration is considered constant, they go ahead and fold it into the Ka value. This is why we call Kas and Kbs. It's not just for acid and base, but it's not just a plain KEQ. It does include the value of the concentration of water. So they're kind of special. And just for a little bit of extra practice, let's write the Kb for ammonium. Again, products over reactants. So we have the ammonium cation, the hydroxide anion. We're putting it over ammonia. And again, the concentration of water is included in Kb. So this is how we either calculate Kas, or you'll find a Ka and you'll calculate something else. I guess the only thing else to point out is why don't the strong ones have Ka? So we can write a Ka, let's write it up here for hydrochloric acid. So that would be concentration of hydronium over concentration of, chloride. That's supposed to be a negative. I wrote it the wrong way. Of the chloride anion over the concentration of HCl. Okay, well, we have a problem here. This concentration is 0. We can't divide by 0. So that is why you won't find values for Kas for strong acids, because your original acid, like your HCl here, is gone. There's no more of it left, so it's considered 0, and we can't divide by 0. Now again, this is all in aqueous solutions. I'm not going to deal with switching over to a different solvent because that's a whole different ballgame. So these are all in aqueous solutions here. Okay. All right. Oh, for a therapist, your test was delayed. Yay! Okay, that's great. It's always nice to have a bonus couple of extra days to study, isn't it? Okay. So now that we have definitions down, it's time to jump into the nitty-gritty and actually start to do the math with these problems, which I know can be a little bit overwhelming. We're going to try and take this step by step. And, again, as you have questions, please feel free to just put a comment, and I'll try to keep an eye on the chat so I can know what's going on. Bad news, the test is all FRQ. Okay, well, we need practice, right, doing the FRQ. So that's not necessarily a bad thing, or maybe I'm going to try to not see that as a bad thing. Okay, well, these are all free response as well. Like I don't have any, multiple choice here, so I'm just going free response as well. Okay, so let's read this question. 5 milliliters of formic acid, and then they give us the formula. They give us the Ka is diluted to 125 milliliters. What is the pH of the diluted solution? And they give us the density of formic acid is 1.22 grams per milliliter. Okay, so we're starting kind of easy. We're starting small. This is just a weak acid in aqueous solution. So we're not reacting it with anything. We're just putting it in solution. So all we have to deal with is our weak acid. And you might ask, hey, how do you know that formic acid is a weak acid? Okay, well, there are two ways I know. One, it has a Ka value. If it has a Ka value, it's going to be a weak acid or a weak base. The other thing is formic acid, if I pop back, formic acid is not in my common strong acids here. So, there are two different ways to kind of figure out that formic acid is going to be a weak acid. Because it's a weak acid in aqueous solution, the first thing I want to do is I want to write my chemical equation. I want to see what is going on with this formic acid. Okay, so again, we have just our formic acid in aqueous solution. So we are going to get hydronium, and then we're going to get, I guess I could take any H off, and then we're going to get the conjugate base of formic acid. All right, so this is what's happening in solution. Again, notice equilibrium arrows. This is really important. If we are going to use an ice table, if we're going to figure out this problem, the first thing I want to know is I want to know my concentration of formic acid. That's my first thing. Oh, so I have some questions. Ice tables are going to be worked. Oh, the ice tables are going to be worked. Okay, that's really nice that ice tables already worked, because we're going to write ours from scratch here. So I want to get the concentration of formic acid. So what do I have to help me calculate the concentration? I know I'm starting with 5 milliliters. I'm diluted to 125 milliliters, and my density is 1.22. Okay. So this is where having strong dimensional analysis skills is going to help you so much. I know that dimensional analysis is something that you do like way at the beginning of the year, the beginning of the semester, and you just kind of skip over it. But I'm going to show you how much your dimensional analysis is going to help you take care of figuring out your concentration in one step. I'm going to do something I call smashing, but all you're doing is you're following your units. So if I want concentration of formic acid, I'm keeping in my mind that I want moles of formic acid over liters of solution. Okay, but that's not what I'm starting with, because I wasn't given that. So I'm starting with 5 milliliters of formic acid. Okay, so my first thought is I gotta get to moles, right? Because molarity is moles per liter. I have a volume of formic acid here. How do I get to moles from a volume? Well, I can't jump straight to a volume, but I do have the density. So I can use the density to convert to grams. So this is going to be 1 milliliter, and this is 1.22 grams of formic acid. Okay, we're still going. I'm not done. Like, this is going to be multi-step here. Okay, so now I no longer have milliliters of formic acid. I have grams of formic acid. I want moles of formic acid. How do I convert grams to moles? I use the molar mass. Let's see. I did write that one down. Here it is. 46.03 grams per mole for formic acid. HCO2H. Okay, I'm still going. Okay, so I've converted now to moles of formic acid. Again, how do I get concentration? I have moles. I divide it by my liters of solution. Well, how much solution do I have? The problem told me. I've diluted it to 125 milliliters of solution. Of course, molarity is per liters. So I could put this in, but I trust you guys know where this is coming from, liters, and if you want, you can put a 1 up here. So see what has happened here to my units. My milliliters of formic acid have canceled, my grams of formic acid have canceled, and now I have moles over liters. So this really is just a dimensional analysis problem, but I know when you read the problem, it feels like, what? How do I do this? This is again why, like, I think it's so important to just have strong dimensional analysis skills. Let your units lead you to the answer that you want. Okay, I did this calculation. What is our concentration? 1.06. And again, this is molarity. This is moles of formic acid per liter. Okay, that's fantastic because we need concentration to do our ice table, although you can do ice tables in moles too, but we're going to do it in concentration. Okay, let me make sure that there are no questions. Still, if you're on ice tables, yes, there's so much to look at. Yeah. So, okay, so we're going to construct our ice table totally from scratch here. I'm going to rewrite my equation because I always like to have my equation at the top of my ice table. Now, some people call these rice tables because you're supposed to write your reaction first. I mean, you know, whatever works for you, it's totally fine. Okay, so ice, I-C-E. Initial, this is initial concentration. All right, I just calculated my initial concentration of formic acid, so that one's easy, right? All right, here's my initial concentration. Remember how water is a constant and it's folded into either your Ka or your Kb, so we don't have to worry about water. I am not writing anything in the water column. I'm just going to leave it completely blank because I don't have to worry about it, which is fantastic. Okay, now initially, how much hydronium do we have? Well, initially we assume that no forward reaction has taken place. So we have no hydronium and we also have no conjugate base at this point. Okay, so that is our initial concentration. That is our I. We put in our initial concentration of formic acid. Everything else is 0. Okay, C is either change or consumed. You know, I've heard it said both ways. We don't know this. So we just know that some amount of formic acid is going to dissociate, but we don't know exactly what it is. So I'm just going to say minus X. So some amount X is going to dissociate. I don't know. I'm just going to call it X. Now, that minus X is because I'm going to be losing some of that formic acid. But if you think about your reaction in your stoichiometry, I am creating hydronium and I am creating my conjugate base. These are all in a 1-to-1 ratio. If by chance you had a 2 here, this would be 2x. So it does follow your stoichiometric ratios, but generally with weak acids and weak bases, these are almost always going to be 1-to-1 ratios, which does help the ice table stay a little bit simple for at least for acids and bases. Of course, you can do ice tables that are more complex. Okay. E is equilibrium. You're just adding down the column. So I'm going to take my 1.06. I'm going to add my consumed, which is minus X. So that just becomes 1.06 minus X. This, you can think of this as 0 plus X if you want, but generally, why keep the 0 in there? We just write these as X. So that's it. That is your ice table done. It's your initial, it's your consumed or your changed, and then it's your equilibrium concentrations. But of course, we're not done with our problem yet, and I'm thinking I'm going to need another page. So once you're done with your ice table, you want to put it into your equilibrium expression. Well, we actually haven't written an equilibrium expression for our reaction yet, so let's go ahead and do this. All right, so formic acid is an acid, so this is going to be a Ka, and it's just products over reactants. So it's my hydronium times my conjugate base, and this is over formic acid, O2H. So again, I'm just getting this from my balanced chemical equation right here. All right, so now I'm going to take my equilibrium concentrations and I'm going to plug them into their appropriate spaces. Okay, so this is still just a Ka. So hydronium is X. Great. Okay, I'll switch to parentheses instead of boxes or brackets. Okay, so my conjugate base, again, here is just X. And then my formic acid, if I go to my equilibrium, is this quantity right here, 1.06 minus X. All right, so I've plugged everything into my Ka. Let me make sure that there are not, there looks like there's some questions. Wait, so hold on. If you add 1 million gallons of water to a buffer solution and the pH wouldn't change, well, as long as you're not changing your ratio of like weak acid to conjugate base, then you should be totally fine with that. But it does depend what else is in solution. So what else have you got in solution? Do you have any other reactions going on potentially that could change the pH of the buffer? Okay, so back to our formic acid. I do, you know what? Hold on. I'm going to give myself another page. I do have a value for that Ka because I have it in the problem right here. So I'm going to plug that in for my value of Ka. That is 1.8 times 10 to the negative fifth. Again, I'm just going to carry over my expression from the previous page, minus x. I did change this to x, that's a terrible x, to x squared. And just so you know where it's coming from, I'm just copying this back down again. I'm taking x times x and making it x squared, and I'm just plugging in my value here for Ka. Just, I know it's tough when the page switches over. Okay, so this is a quadratic. I really don't want to have to use a quadratic equation. What I'd really like to do is just drop this term right here, because then I can solve for x so much more easily. Now, sometimes you can drop that minus x, and sometimes you cannot drop that minus x. But you need to run a couple of tests to see if you can simplify your equation, or if you're going to have to bite the bullet and go through the whole quadratic equation. So I'll show you both tests. Now, a lot of people just use the 5% rule, which is totally fine. But there's a test you can run at this point before you have solved for x to see if you can drop the minus x that I like to do. So I like to run both. Okay, so this first test, what I'm going to do, it's my initial concentration of acid over Ka. And if that is greater than 500, then I can drop that minus x term. Okay, so my initial concentration was 1.06. This is, of course, of my acid. My Ka was given to me 10 to the negative fifth. Again, I want this to be greater than 500. So when I run this, I get 5.9 times 10 to the fourth, which, yes, is greater than 500. So I put a yes over here, which means now I can get rid of that minus x term. So I get to simplify this equation to simply 1.8 times 10 to the negative fifth is equal to x squared over 1.06. Okay, that's a lot easier to solve. We don't have to go get the quadratic equation. Let's just go ahead and make sure x is negligible. Yeah, so that's what we're testing, because again, sometimes it's not and sometimes it is. Now, seeing that the Ka is 10 to the negative fifth, a very quick and dirty rule of thumb is if you are smaller than 10 to the third, you're usually okay dropping the x. And if you're bigger than 10 to the negative third, then you probably don't. And like if you are 10 to the third, you better test it, because you're probably like on that borderline. But this is why I like to just go ahead and run these tests. They're pretty simple. They don't take a lot of time. And then you can be sure moving forward that, yeah, you can drop that minus x, or no, you can't drop that minus x. Oh, anything less than 10 to the negative fourth. Yeah, alongside the 5% rule. And once we solve for x, we're going to go through the 5% rule too. So I show both kind of this initial rule that you can apply before you have solved for x, just to see if you can drop it. I like to know if I can't drop it before I actually run through that calculation, so that I'm not wasting my time doing a calculation that I can't use anyway. But again, it just, whatever kind of you want to do. And yes, sometimes teachers put limits and they say, okay, don't worry about calculating that. If it's, smaller than 10 to the negative fourth, you can drop it, no problem. Okay, so we still haven't solved for x yet. All right, but this is trivial to solve for x. So let's solve for x. So x at this point is 0.00437. Okay, so that is solving for x. And let's go ahead and run our 5% rule just to make sure that our approximation is correct. So that is going to be your value of x over your initial concentration times 100%. This should be less than 5%. So my x value is here, 437, again, over my initial concentration of acid times 100%, looking for less than 5%. And when I did this calculation, I got 0.41%. So yeah, definitely less than 5%, which just confirms again. So both of these tests are telling me, yeah, you can drop it. Plus we got 10 to the negative fifth. So probably, yeah, we can drop it. Okay. So, oh, she never showed that method. Yeah. So a lot of times teachers will, will show the 5% rule. I mean, this is really a percent dissociation, but they don't show the first rule. I don't know if the first rule really has a name. I always call it the 500 rule, but I don't know if that's actually the name. But again, if I can run a test before I have to solve for X, I'm totally going to do that. Okay, so we have confirmed that yes, our value for X is valid. We have solved for X. And now we have to keep in our mind, okay, so we have solved for X. What is X? What did we just solve? So I've got this number here, but I have no unit with it. What is it? What is it associated with? What have I actually done? Okay, so I've got to go back to my ICE table because that's where I introduced the value of X. So what is X? Well, X is my concentration of hydronium. It's also my concentration of conjugate base. I can also use X here to calculate my final concentration of formic acid. So X is how much here we have changed. So I'm going to come back to my page here and I'm going to be really specific. Here's my value for X. This is my concentration of hydronium. Okay, I want that concentration of hydronium. Why do I want that concentration of hydronium? Because I want to calculate pH, and pH is negative log concentration of hydronium. So I feel like this step right here is often a disconnect for students because they work really, really hard to solve for X, especially if you're solving for the quadratic, and then they forget what X is and how it applies to the problem. So always make sure you go back and you're grounded in what your problem is and what's going on chemically. Okay, so now really we've got a trivial calculation here because we're just going to do the negative log of 0.00437. And that gives us a pH value of 2.36. Now, does that make sense that we would have a value of 2.36? Well, let's remember we have formic acid in solution. So we have an acid in solution. So we should have a low pH. We should absolutely be less than 7. So having a pH of 2.36 makes sense. So again, it's easy to get lost in all of this math and writing your ICE table and getting everything in, but make sure you stay grounded in what is happening chemically so that if something isn't working or maybe you've miscalculated something, you get a little bit of a red flag saying, hey, wait, this doesn't make sense with what is going on chemically. Okay. All right. So I'd probably be in jail. Yeah. Okay. Yeah. No. Let's not go to jail. That would be good. Let's stay and do more chemistry, right? Okay. So let's go on to our next problem. I'm already seeing there's. I get so excited. I put all these problems in and I never get to all of them. Okay. So diazepam is a weak base with a pKb of 2.92. It's used to treat symptoms of alcohol withdrawal, panic attacks, and anxiety. So this is Valium, or what Valium was now. Of course, it's generic. Okay, what is the pH of a solution with 30 grams of diazepam dissolved in 150 milliliters? Okay, so we have a weak base in aqueous solution. Again, we only have the weak base in aqueous solution, so we don't have to deal with any other chemical equations going on, which makes things simple because if I get to my final problem, we're going to do a reaction of an acid and a base, but we're just focusing here on a base. So this is going to be very similar, but not exactly the same as the previous problem. We've got equilibrium happening. We know we're going to use an ICE table, but first, let's get a chemical equation going. Okay, so this is kind of a monster, and I am not going to want to write the equation for diazepam the whole time. So let's go ahead and write it out at least once. 13CO N2O, and let's pop an H on the end plus OH. All right. So this is the equilibrium that's happening in solution. I'm going to simplify this equation just because I don't want to have to keep writing diazepam out. So I'm going to go with the generic base for B for base plus water gives me base and a hydrogen plus hydroxide. So this is just going to be a lot easier to handle, and then I'm not having to deal with writing that molecular formula out. Okay, so just like before, I need to get concentration, and I need to get concentration of my base, my diazepam. But of course, I don't have concentration. I have got to figure concentration out. So what do I know? I know I've got 30 grams of this, and I know it's dissolved in 150 milliliters. So this one is a little bit easier because we're not having to deal with density. It's still a dimensional analysis problem, but it doesn't have quite as many steps. Okay, so let's start with our 30 grams. Again, I'm just going to call this B so that I can save time writing. For concentration, I'm getting to moles of my base over liter. So that is where I'm headed. That's where I want to go. Right now I have grams, so I need to convert grams to moles. I do that with molar mass. So the molar mass of this thing is fairly large, as you would expect, over 1 mole of base. Okay, great. So I have converted from grams to moles. Now I need to divide by my liters. Again, I'm going to skip a step here. This is 150 milliliters. I'm just going to write this as 0.15 liters. And if you want, so you don't leave that space empty, put a 1 there. That might help just keep everything checked. Okay, so just making sure. Grams have canceled. Now I've got moles over liters. That's molarity. So I know students don't like to write units in when they do calculations, but I'm telling you, your units are going to save you so many times. Make sure you're writing your units in so that you know you have done the calculation correctly, because I know that I have graded papers where a student has done a lot of work and it's done very well, but they'll get a conversion factor flipped because they haven't written down their units. So that's very frustrating actually for both of us. Okay. Oh, okay. So when it's ingested, I guess I missed the first part, the pH of the stomach. So yeah, so OG benchmarks is totally right. So remember that your stomach is not a static situation. It's not a closed system. So we have diazepam here, and basically what I think of as a beaker or maybe a flask, so nothing else is happening. But once you introduce things to the body, all sorts of things happen. I will let OG benchmarks talk about that because he is a medicinal chemist. But no, we can't... yeah, you can't just say, oh, well, things are going to change because the body's constantly making more acid. Okay, so back to diazepam. We just have it in a beaker. We have not ingested this. We have our equilibrium equation. We have our concentration of base. So now I want to go ahead and do my ice table. I'm going to rewrite my simplified equation because, again, I tend to make my ice tables rice tables. Okay, so BH plus OH. All right, so now ICE. Again, initial change equilibrium. So initially, what is my concentration of B or my base? Well, I just calculated that. 0.702 molar. Again, water, we just ignore. We don't do anything with, which is nice because I needed that space right there. And again, initially, this is before any forward reaction has happened. So we don't have any protonated base and we don't have any hydroxide. So those are just 0. All right, so that is our initial row taken care of. Now we want to take care of our change or our consumed, however you think about it. Again, I don't know how much base is going to get protonated, but I know that some is. So I call that X. So I am going to lose some amount of my base on my reactant side because my forward reaction is happening. And then I'm going to create a certain amount of protonated base and a certain amount of hydroxide here. Again, I don't know what it is. This is why I call it X. Now for equilibrium, you just add down the column. So I have 0.702 minus x. Again, I've just added my I and my C values. And then for my protonated base, my hydroxide, the same thing, except I'm not going to write 0 plus x. You can. I'm just going to write x on each. Okay, so that really looks like a y. Let's make sure that's an x. So this is my ice table. Okay, that's fantastic, but I am not done with this problem and I need another page. So let me get myself another page. Okay, so my ice table is done, but I have not put any of my equilibrium concentrations into my expression for Kb because I haven't written an expression for Kb yet. I think it's best to just go ahead and again write my chemical equation up here on my second page just so I keep track of what's going on. All right, so there's my chemical equation. Now I'm going to write my Kb. Again, this is a Kb because we have a base. But still, we're going to fold that concentration of water into the value of Kb. So we don't have to worry about it, which is nice. I mean, that's fantastic. I love any simplification that we can do. So again, just products over reactants. And the nice thing is these are all one-to-one, so that does help with the math and makes it a lot simpler than if you're dealing with a different kind of equilibrium. Okay. So I'm going to have to go back and forth a little bit here. So what I'm going to do is I'm going to take each of these equilibrium concentrations and I'm going to put them into their appropriate places in my Kb right here. So for my protonated base and my hydroxide, those are both just x. Again, I'm just pulling from my equilibrium row down there. And my base here is 0.702 minus x. This is equal to my Kb. Okay, great, fantastic. But here again, I am going to run my test because I really want to drop this negative x. Now, based on my pKb, actually, we should go ahead and convert pKb to Kb here because that's maybe not something that you can do straight in your head. So let's go ahead and do that. So pKb is negative log of Kb. I know my pKb is 2.92. So now I'm just going to do the anti-log and I'm going to solve for Kb. And I get 1.20 times 10 to the negative third. Okay, so this is a borderline case. 10 to the negative third tends to be borderline. So we really do want to rely on our test to see if we can drop that minus x or if we're going to have to suck it up and go through the quadratic equation. So let's run our test. So this is, again, kind of what I call my 500 rule. So my initial concentration of base over Kb should be greater than 500. So this was 0.702 over, I've just calculated my Kb here. And that is something that is classic for teachers or like the AP exam or the IB exam to do, is to give you a pKb when you need the Kb and just make you convert it. So just kind of FYI. Okay, so this is really close, but it is actually greater than 500. So we can drop that negative x. And for this one, again, because we're so close, we will definitely come back and confirm with our 5% rule as well, just because we're borderline here. All right, so this is going to simplify. I'm going to plug in my value for Kb. Oh, yep, here it is right here. 1.20 times 10 to the negative third equals x squared over 0.702. So this, again, is a lot easier to solve than having to plug everything into the quadratic equation. So what is our value for x? Is 0.0290. Let's check our 5% rule because we've just solved for x. Again, x over our initial concentration of B times 100% should be less than 5%. So let's see if this is okay over my initial concentration. What was my, oh yeah, 0.702 times 100%. Again, hoping this is less than 5. And we get 4.1%. So again, borderline, but yes, this is true. So we are okay with dropping that minus x. Okay, great. So we, again, this is the same place that we had in the last problem. We've solved for x. What is x? What does this have to do with anything? How do we use this to solve our problem? We've got to go back and ground ourselves in our chemistry. Now, what is x? Okay, so we used x in our change column here. So remember, x is your concentration of protonated base. X is your concentration of hydroxide. You can use x to figure out your concentration of your diazepam that is left in solution. We are trying to find pH, so I'm mostly concerned with this column right here. Okay, so this equals my concentration of hydroxide. All right, so that's really important to make sure you write it down. What is X? What are you using? Because this is another place where students kind of, if they're not writing down and they're not thinking about what's going on chemically, then they're going to assume that X is hydronium. And the next calculation they do correctly, but instead of realizing that they're calculating POH, they think they're calculating pH. And that's a problem. Okay, so let's calculate POH first. So my POH is 1.54. Again, if you haven't gone back and really thought about what your X is, and this is concentration of hydroxide, and you move forward with this calculation thinking that you're calculating pH, hopefully there is a red flag kind of waving at you so that you can go back and make your correction. Because if I said I had a pH of 1.54, but I have a base in solution, hopefully I go, wait, that doesn't make sense. I need a pH that is greater than 7. It might not be much greater than 7, but it's got to be greater than 7. So again, make sure you stay grounded in what's going on chemically and ask yourself, does this make sense with the system I have? Okay, so it makes sense to have a POH value of 1.54 because that means your pH value is 12.46. Yeah, we got a base in solution. We should have a pH that is greater than 7. I'm going to box this so that if it is graded, then my teacher or my professor can find my answer quickly. Okay, so let's see if there are any more questions. Oh, okay. Yeah. No, I think we're good. All right. How much time do we have? All right, we can do a little bit of my next problem because this is what's going on when you've got a neutralization with, in this case, a weak acid and a strong base, which means you've got to deal with your stoichiometry and you've also got to deal with your equilibrium. I'm not going to make it through this problem because it's just going to take too long. But let's get it started and let's just see how far we can go. All right, so first reading. So we've got a 20 milliliter aliquot of 0.150 hypochlorous acid, and they give us a molecular formula. They give us a Ka. Is titrated with 0.075 molar solution of potassium hydroxide. How many milliliters of potassium hydroxide? Oops, that should be R needed to be added to reach the equivalence point. Okay, so we need to figure out where the equivalence point is. What is the pH at the equivalence point? Okay, because this is not a pH of 7. We don't have a strong acid and a strong base. And then what is the pH of the reaction 1 milliliter before the equivalence point? And then what is the pH of the reaction 1 milliliter after the equivalence point? Okay, so and this part down here is to show when you're titrating, the pH changes very rapidly around the equivalence point, which is why you need to either go dropwise or honestly, when you're really close to the equivalence point, I like to split drops. Okay, but that's titration technique. We don't need to go into that right now. All right, so what is going on chemically? Let's get our balanced chemical equation. So we have hypochlorous acid plus potassium hydroxide. That is being neutralized. We're going to make a salt and we're going to make water. Okay, so this is our chemical reaction. It is not in equilibrium. This is a forward reaction only. So in any titration, if you have either a strong base or a strong acid, it is going to drive the reaction forward and forward only until all that strong acid or strong base is used up. So as long as we've got KOH in here, that's reactant, we only have the right reaction. All right, so what we need to do first is we need to figure out how many milliliters of potassium hydroxide are needed to reach the equivalence point. What is the equivalence point? What is going on at the equivalence point? Because that is how we're going to determine how many milliliters of potassium hydroxide we need. So at the equivalence point, so we'll say at equivalence. Now, this is equivalence. This is not endpoint. So remember, endpoint is where the color of your indicator changes. An equivalence point is a stoichiometric calculation. Now, ideally, your endpoint and your equivalence point are close enough that they can be considered the same or close enough, but they are actually not the same thing. So at the equivalence point, my moles of my acid should equal my moles of my base. Okay, so that's what's happening at the equivalence point. My moles are equal. So do I know either one of these moles? Do I know either can I get to my moles of acid or can I get to my moles of base? Well, just from the wording of the problem, I'm guessing I cannot initially get to moles of base because it's asking me how many milliliters of potassium hydroxide I need. So I'm guessing that that is going to be more difficult. So can I potentially get my moles of my weak acid, my hypochlorous acid? Well, let's go back and look and see what we've got. So I know I have a 20 milliliter aliquot. That's just a 20 milliliter sample. I do know the concentration of my acid. I also know the concentration of my base. Okay, so those are all really helpful at this point. So I can't get my moles of potassium hydroxide, but I can get my moles of weak acid because I have a volume, I have a concentration, I can get that moles. So I'm going to start with my concentration. Remember, molarity, moles per liter. So I'm just going to write this as really, I think of these as complex units as a fraction. So that is molarity. So you can take that 1.5 molarity and you can always break it apart into the constituent units. And that's often very helpful because in this case, I want my volume to cancel. So you can see my liters of solution cancel. And now I've just calculated moles of hypochlorous acid. And I have 0.003 moles of hypochlorous acid. Just to be clear, this 0.020, that's the 20 milliliters right there. Okay, so that is my volume of acid. Okay, yeah, no questions. Just wanted to make sure that we were still good. Now remember what I said, my moles of hypochloric acid equals my moles of potassium hydroxide at the equilibrium point. So I also have 0.003 moles of KOH at the equivalence point. Okay, so this is good. So now we have converted from our acid to our base, which is good because I need to get milliliters of base here. So I have my moles, I have a concentration, I can get to a volume. All right, so same thing. Here are my moles of potassium hydroxide. Again, really, this is all just dimensional analysis. It really, really is. I've got my concentration. Again, I'm going to write it like this. So I split apart the concentration into liters and moles. 0.075 moles of KOH. And then because we want milliliters, I will throw in a milliliters conversion. Of course, you don't necessarily have to write that out because at this point you're probably very comfortable with converting between liters and milliliters. But you can see, again, all my units have canceled except for my milliliters, and that's what my question asked for. So, units are so helpful. And this gives us 40 milliliters of KOH. Okay, so that is how many milliliters of potassium hydroxide I need to add to my sample of hypochlorous acid to reach my equivalence point. Okay, so that is the first part of the question done, but I am not done with the equivalence point because I need to say what is the pH at the equivalence point. Now, if this was a strong acid and a strong base, that would be very easy because at that point you just have a salt with no acid-base properties in water, and your pH is 7 because your pH is dominated by water. But that is not the case for this situation right here because I have a weak acid in solution. And what happens when you have weak acids in aqueous solution? Okay, yeah, they make hydronium, but they also make conjugate base right here. So I have the conjugate base of hypochlorous acid in aqueous solution. Well, what is true about the conjugate base? It is a weak base. All right. Now, so if you look at, just to compare this, if you look at a strong acid, okay, granted, it's not in equilibrium anyway, but the conjugate base of hydrochloric acid has no acid-base properties. So no acid-base properties. So it is not a weak base in solution. It's just part of a salt. You can think of it as a spectator ion. It's just going to hang out, kind of like in this case, our potassium here. Potassium is just totally a spectator ion. It hangs out. It has no acid-base properties. But we do have to deal with the conjugate base of our hypochlorous acid because it does have acid-base properties. It is a weak base. Okay, I need another page. Here we go. All right, so let's write our equilibrium expression for our conjugate base of hypochlorous acid. So we have our conjugate base. It is in aqueous solution. So what do bases do? They accept protons. And we have an equilibrium problem brewing here. All right. So we need to do an ice table or a rice table for this equilibrium expression. Okay, so ICE. Okay, for this one, just because we've already calculated the moles, I'm going to use moles in my ice table. Again, usually we use concentration, but you can also use moles. So I'm just going to shake it up here and use moles. And I'm doing that because I have calculated my moles of acid here. So remember, this is a 1-to-1 ratio. So at the equivalence point, I have used 0.003 mole of potassium hydroxide, and I have used that many moles of hypochlorous acid. So just think stoichiometrically. If you used 0.003 moles of your conjugate acid, how many moles of your conjugate base, I should really circle that, have you produced? 0.003 moles of your conjugate base. Remember, these are all 1-to-1 stoichiometric coefficients, which does make our life really, really easy. And that's why for this ice table, I'm going to go with moles because I already know how many moles I have. But of course, you can calculate concentration too. Okay, so starting with how much conjugate base I have. Again, remember, I'm getting that from my stoichiometry, from my weak acid, from my neutralization reaction. We're treating this like any other ice table. We're going to say initially, we haven't formed any of our hypochlorous acid or any of our hydroxide. We only have our conjugate base. For our change, we're going to use up some of our conjugate base. We're going to form some hypochlorous acid, and we're going to form some hydroxide, but I don't know how much. Now for my equilibrium, I'm just going to add down this column. 0.003 minus x. This is x. This is x. So hopefully this is looking a lot like what we did in our first two problems. I'm just going to write a KB for this. Again, just products over reactants. Hydroxide over our conjugate base. Again, remember, water is folded into your KB. Let's put in our values here that we got from equilibrium. So this is x, and this is 0.003 minus x. All right, so fantastic, but we have a little bit of a problem, don't we? What is this KB? So all I have is a Ka for hypochlorous acid. So it's not like I've got a pKb for my conjugate base to work with. So how do I take my Ka of my weak acid and possibly get to my Kb for my conjugate base? This is where having conjugates is helpful, because remember, with conjugates, your Ka times your Kb equals, that's a W, equals Kw. Now, this is only true for conjugate pairs. So you couldn't take your Ka for hypochlorous acid and calculate your Kb for diazepam. So it's only for conjugate pairs that this works. Again, so I know my Ka. My Ka for my weak acid was 10 to the negative 8th. I don't know my Kb. I'll know it in a second. And of course, Kw is 1 times 10 to the negative 14th. This, again, is another way to take, I don't want to call these simple problems, but to take a problem and make it just a little bit more difficult, is you're only given the Ka of the weak acid. And really, when you do this, if you're going to do these kind of reactions in lab, you go to a table of Kas. You could probably find tables of Kbs for conjugate bases, but usually you don't. You just go and look up either Kas for acid or Kbs for bases. So this is very common to do this calculation. Okay, so 2.87 times 10 to the negative 7th. All right. Because we're running low on time, I'm just going to tell you that, yes, we can drop this minus x. This is dropped just to save time, so at least we can get through calculating our pH at the equilibrium point. All right, so I have my value for Kb. I just calculated it. 2.87 times 10 to the negative 7th. This is x squared over 0.003, so I can calculate x. X equals 2.93 times 10 to the negative 5th. Again, I got to make sure I connect that value of x with what is going on physically. So I go back to my ice table. I'm less concerned with my acid here. I'm more concerned with my concentration of hydroxide. But I did a little bit of a twist, and I should have written this in. Remember, I used moles here, not concentration. This is where you can run into problems if you don't always use concentration. So just be aware, choose the way that you feel like is going to make sure you make the fewest mistakes possible. All right, so this equals my moles of hydroxide, not my concentration. So I've got to be careful about that. I'm going to come up to here. So to calculate my concentration, of course, I'm going to take my moles, 2.93 times 10 to the negative 5th, moles of hydroxide, and I need to put this over liters of solution. So let's go back to the original problem. I started with a 20 milliliter sample, and I have added 40 milliliters of potassium hydroxide. So I have a total volume right now of 60 milliliters. So this is additive, and maybe what I'll do is I'll go 20 milliliters plus 40 milliliters equals 60 milliliters, which of course we need to convert to liters. Okay. So hopefully that is clear. I kind of smashed that in there. My concentration of hydroxide is 4.89 times 10 to the negative 4th. That is molarity. So first I'm going to calculate my pOH. Now, of course, if you like, you don't have to calculate pOH and convert that into pH. You could also take your concentration of hydroxide and convert it straight into concentration of hydronium. I'll write this over here because remember, your concentration of hydroxide times your concentration of hydronium equals 1 times 10 to the negative 14th. So just FYI, you don't always have to do it this way. Do it whichever way makes the most sense to you, whichever way you like doing it. Okay, so my pOH is 3.31, which means my pH is 10.69. Okay, so does that make sense to have a pH that is above 7? Yes, because I have a base in solution. Granted, it's a weak base, but I have a base in solution. So you can see the difference in pH between having the equivalence point for a strong acid and a strong base where your pH is 7. And here we have a strong base but a weak acid. And just having this conjugate base here pulls the pH up quite a bit. So if you look at titration curves and you just look at the shapes and where those equivalence points are, you'll see a big difference between like the titration of hydrochloric acid and sodium hydroxide versus a titration like this. Definitely the equivalence point is usually raised up if you have a weak acid, and it's dropped down if you have a weak base. Okay, I know it's 8 o'clock and I feel like my voice is kind of starting to go. So if you have other questions, if you want to see other topics, please let me know. You can leave me a comment. You can leave me a comment here. Does the autoionization fit? Yeah, autoionization of water. It depends on the strength of your weak base. But remember, when you do your KW here, it's 10 to the negative 14th. So at this point, we can assume that our conjugate base here is dominant and we don't need to worry about the autoionization of water. But in some cases, you do have to worry about the autoionization of water. And again, strong acid, strong base, autoionization of water is your only acid-base equation that's going on. So that completely dominates. So I would say it's a case-by-case basis, honestly, depending on what your conjugate base is and how strong your conjugate base is. But yeah, if there are any other questions, especially if you've got questions after the live stream, just you can leave me a comment in this video, or you can leave me a comment on Facebook, or you can shoot me an email. That's totally fine. But yeah, I want to make sure that I am delivering content for what you need right now for where you are in your classes. So just let me know what you want to see, and I'm happy to work any kind of chemistry problems. But thanks so much for joining me tonight, and I hope to see you guys next week. Bye.